No. I want to do all this and get a magic bullet. Come on. I'm going to give something that like makes your liver to stop functioning the way it's supposed to. Come on. And you're going to expect nothing bad to potentially happen? Stupid. It's stupid.
Not yet. Okay. You progressed.
There's a code over there. And believe it or not, I have a PowerPoint presentation. Right? So.
Is it on Blackboard?
Not yet, but I'll put it up there.
I got it.
All right, so where did we leave off on Tuesday? Because we were just about done going through the regression code and all that stuff. We never seem to have enough time.
I think Tuesday we were going through the assignment and all the assumptions.
The assumptions, but where did we stop?
Oh.
Leverage, all right. Oh, that's good, because then we're almost done. I get bored of this after a while.
That's especially
So what I'd really like to do today is finish up multiple regression and then start a nova. Start a nova. That's what I'd really like to do today. All right. I think we were somewhere about here-ish. All right.
Yes, I can. You can see something like a wild man.
Okay, so this plot that we're looking at here was generated using this LVR2 plot. All right, so I'm going to look at a leverage plot. All right. So this is, I think, a pretty awesome feature of Stata. Well, let's sort of explain what's going on here, right? All right. So we talked about leverage on Tuesday. We talked about normalized residuals too. Okay. All right. The reason we're interested in talking about normalized residuals is that it allows us to think about them in terms of z-scores, right? Well, one thing we're going to do here on this plot is we've squared the residuals. That way, everything is positive. All right. So if we recall, leverage, an observation that has leverage can change the slope of a line, right? So there are two observations in general here that are most worrisome to me in looking at this leverage plot, right? I'm interested in looking at observation number 540. Because even though its residual isn't very large, it's damn near zero, and this is a squared residual, it still has potentially a lot of leverage. Does that make sense? So I can't look at leverage and the residuals sort of independently. Right? I can have a very large residual, but if that residual doesn't have a lot of leverage, it's not going to change the parameter estimates. Right? So what I'm going to do is I'm going to be interested in looking at this value here. This is observation number 540. So when you do that LVR2 plot, it plots out the observation numbers for you, which is kind of cool. I think it is. The other thing that I'm interested in looking at is this variable here. This observation, we've done a very poor job of predicting this observation, right? But if I look at it at the leverage of this observation, it's not terrible, right? So even though this is an outlier with respect to a y variable, it doesn't appear to be exerting too much effect, too much influence on the parameter estimates. So what I would do is I would, one by one, is I would go back and I would probably go back and redo my regression, and I would drop observation 548 from the data, rerun the model to see if the parameter estimates change in any substantive way, and I would do the same thing for observation 540. And then we can talk about variables having, a high leverage value, but it may or may not change the
Can I ask you a
parameter.
technical question? When you run the regression without that, how do you actually do you say run like?
Yeah, okay.
Yeah. Or do you actually delete it? Hold on.
All right, so I would do regress, time, PRS, try, L, and deal, stress, if n not equal to, what was it, 540?
Yeah.
5.
Is it 2 equal signs or 1 equal sign?
Well, this is a bang. This is exclamation point
It's
not
not
equal 540. So when I run that, I hit there and, oh look, my R square is not going to change a whole lot. These didn't change very much. They didn't change appreciably. I think maybe the effect of stress in this example changed a little bit. Off the top of my head, I don't recall. But all in all, these variables that, or these observations that we observe as being outliers and or having potential leverage, they don't seem to be exerting a whole bunch of, they don't seem to be exerting too much effect. They don't have too much effect on the parameter estimates. In particular, I would be interested in variables up here, or observations up here in this quadrant, right? Which, if you think about it for a moment, variables are observations that are in the upper right-hand quadrant. These are going to be observations that have a lot of leverage and are outliers. Does that make sense? So the variables that would be, that if there were observations here, these are the potential troublemaker observations. But all in all, these aren't too bad. But it's a good idea to say, well, I'm going to look at the most aberrant values anyway. And they don't appear to have too much effect on the parameter estimates. Okay, and then finally, the last thing I might be interested in doing, particularly if I'm interested in doing multiple regression and I want to, quote, control for things, I might want to do these AV plots. All right? So let's, to get us some sense as to what these AV plots are doing, let's actually look at these values. So this is mathematical notation. This is the expected value of physical health given X. What is X? X are the other predictors in the model. So this is the expected value of physical health given mental health and stress, which kind of sounds like a partial variable. And this is the effect of, or time, number of times been to the physician, given X. This set of X is the same given X is here. So this is what we refer to as a partial plot, right? So if we were to remove the effect of, or we were to control the effect of mental health and stress, and we want to look at the effect of physical health on number of times been to the doctor, controlling for these variables, this is what it looks like. So we partialed out the other predictors in the model, and this is a scatter plot of the two partialized variables. Does that make sense? No? Yes, no, maybe? Potentially?
Just repeat it again.
Okay, so we have to go back to the concept of partial correlations. So when I talk about a partial correlation, that means it's the relationship between x1 and y after I've removed the effect of x2 and x3 from both of those values, right? That's what this is. So this is the effect of physical health on number of times been to the doctor holding stress and mental health constant. So that's a difficult thing to say to somebody. What does it mean to hold something constant? When we use words to describe these phenomena, it's difficult. But if you show them a picture, you can say, even after holding these things constant, we can see that physical health, the greater the physical health, the number of expected times you go to the doctor tends to increase, right?
So in looking at this, would it be fair to say that there is a relationship between physical health and stress, but because the slope of mental health is almost horizontal,
Flat,
that it's
right?
not?
It has no effect after we take into account stress and physical health.
Okay.
Yeah. So this is a plot of holding something constant. What's the relationship between X and Y?
Are
So
these the same as the AV plots?
this is an AV plot. It just goes by a couple of different names. It's called an AV plot. AV, they call it an added value plot. That's why they say AV. Traditionally, it's called a partial plot. Okay. But I do believe, one of the things that researchers have a very difficult time doing is communicating concepts to lay people. So you talk to somebody who's never taken a math course, never done statistics, never done research. What do you mean holding something constant, right? Well, you can say, well, this is what this means, After I take these other things into account, look, we still see a positive relationship. And they tend to get pictures. People get pictures a lot easier than just a table of numbers or a bunch of gobbledygook words, because that's what it sounds like to them. Right? I'm sure that's what I sound like to you a lot. Yeah, got it.
That's what I'm hearing.
Yeah.
So when you run a regression, do you just, after you run the regression, can you just write AV plots?
Yep.
And it'll take whatever you just did and divide it up into all the different...
Right. So, the other thing, but now this is now back to bivariate correlation, right? All those assumptions that we had with bivariate correlation still hold. Things like errors are normally independently distributed with an expected value of 0 and constant variance, the homoscedasticity assumption, all that stuff still holds. So up until this point, I think we sort of threw out a couple of assumptions. We said that the data don't satisfy, or our data don't satisfy the assumptions of our model. So I think in looking at the previous plots, we don't have normally distributed error. I think it was positively skewed. We don't have constant variance. I think we agreed that we saw that as X gets larger, the variability tended to increase, so it had that classic fan shape, right? So the homoscedasticity assumption was violated. What are the consequences of violating these assumptions? What would you write? What is your takeaway? Now that you know this stuff, the question I'm going to ask is, so what? So what your error is not normally distributed? So what that you don't have homoscedasticity? What does that mean? Right? That's sort of the important question.
I mean, it tells you that your model is not best suited to answer your question.
There's probably a better model. Your model may not be very good. What else? But why is your model not very good?
If you didn't take into account all the variables or the most important variables, put in variables that.
Well, I guess if you violated the assumption of the statistical test, you just can't. I don't know. Like, can you just not trust at all the assumption? So you don't even know X at all.
So we talk about confidence intervals, right? And confidence is a psychological thing, right? It really is a psychological concept. So if I have data that look like this and my model does not fit the data or the data don't fit my model, we talked about either the model's wrong or the data are wrong. And chances are what's wrong? The model's probably wrong. If that's the case, then the confidence I'm going to have in making any kind of prediction from this model isn't zero, but it's going to be lessened, decreased. Does that make sense? All right? So that is to say, we probably don't want to throw the baby out with the bathwater. You get that expression? That expression, right?
Translate that one for you. I think that.
We don't want the perfect to be the enemy of the good. That's Voltaire. You ever hear that one?
Yeah.
That's Voltaire. We don't want the perfect to be the enemy of the good, right? But we don't want to go out and proclaim that we've proven something, right? We don't want to say this model describes a moderate amount of the variance. No, it doesn't. Because the higher you get up on X, the worse your model does, right? So in this case, because our model our belief about the world doesn't agree with the world, with what we observe, the data, we have to be tentative. And this is where, you could say a better model should be fit in the future. And then you start thinking about what kind of model, based on what you observe, might better describe the data. Did you miss any variables? Go back to the drawing board and rethink your model of the world. Did I miss any variables? Or maybe I should have age squared. Remember, what's his name who sits over here? Dave was talking about transforming the data. That gets to the idea of properly having specified the functional form of the relationships between the variables. So maybe it's not just physical health. Maybe it's the square root of physical health, or physical health squared, or whatever the case may be. All right? But based on this model of the world, here are the conclusions. Here are the inferences. It appears that controlling for mental health and stress, physical health appears to have the greater the number of physical symptoms you have, the more likely is that more times you're likely to go to the physician. Holding physical health and stress constant, mental health doesn't appear to have any effect on the number of times you've been to the doctor. However, and the same thing would be like for stress, right? However, we have seen serious violations of the statistical model. Therefore, these conclusions should be taken with a pinch of salt. More research needs to be put into this. Perhaps a different model should be considered to describe to explain the phenomena of doctor visit going or utilization. Or something like that. But the idea here is, just because the computer spits out a number doesn't mean that it's like you're done, right? It's how much confidence do you have, and it's your job as the researcher to be able to convey and talk about how well your model did, where were the potential problems, and then where do you go from there? Make sense? Okay. All right. Now we're not, even though I'm done talking about least squares regression, we're really not done with it. Because as I said yesterday, what we're going to talk about today, the analysis of variance. Every ANOVA is a regression, but not every regression is an ANOVA. Okay? So the ANOVA is a subset of regressions. Okay, all right. So, all right. Just as a shocker, I have well, from there. Okay, so today I want to start talking about ANOVA. Okay, so ANOVA is an acronym for the analysis of variance. Analysis of variance. So let's talk about this here for a second. Let's talk about the title of this. One factor. Okay. In ANOVA language, in ANOVA jargon, we refer to our independent variables as factors. Right? Factors are discrete variables. They're usually categorical. Like treatment 1 versus treatment 2 versus placebo. Right? So I have 3 levels of my treatment factor. Right? So the number of factors tells me so I could have a 2-factor fixed effects ANOVA, in which case I would have 2 predictors, and each of those predictors would have 2 or more levels, right? So the other thing that we talked about before was this concept of fixed effects versus random effects. In this case, when we want to compare, when we're only interested in comparing, this group versus this group versus this group, that's the universe I'm interested in making my inferences about, then we can refer to these factors that we're studying as fixed, because in some sense, we have sampled all of the things that we're interested in sampling from. Drug A, drug B, and a placebo. There might be other drugs, but I'm not interested in that. Right? Makes sense? Okay. ANOVA. So hopefully we should be able to go fairly quickly through, I hope, through this. This should be a review of what you ended with-ish last semester. All right? Okay, so with the ANOVA, the ANOVA is an extension of the t-test, right? If we want to compare the means of 2 groups, we can use an independent samples t-test. The ANOVA is a generalization of the t-test in that we can use the ANOVA to compare the differences between 2 or more populations. 2 or more. So even though if I have 2 groups, I could still do an ANOVA. Right? I could still do an ANOVA. And I could actually get the same p-values if I did a t-test. Okay? All right. So when I want to compare 1-factor groups that are nominal, categorical, and my outcome is continuous, I want to compare the means of 2 or more groups, I'm going to be interested in doing an ANOVA, the analysis of variance. Okay? So let's deal with a situation here. So here's an example situation. So say, we make dermatologists in here? No? Good. All right. So we're going to talk about blisters. The blisters on my finger. Any Beatles fans? No? I got blisters on my fingers right now. So you have 25 patients. They all present and are randomized to one of 3 possible treatments to treat their blisters, right? So the treatments that we're going to look at are treatment A, treatment B, and placebo, right? Right? Because of confidentiality, we can't talk about what treatment A, treatment B is, so we'll just use them as a motivator, right? And I'm interested in looking at the number of days until I'm blister-free, right? So here are the data. So for the number of people who are randomized to treatment A, here are the number of days it took for them to become blister-free, with a mean of 7.25 days. The data for people receiving drug B, 8.875 days. And then for the people in the placebo, 10.1 days to blister-free. Okay? So if I were to start writing down a hypothesis, right? That's actually where I should start, right? How do you think I would rate a hypothesis for this? Like a null hypothesis?
In the null hypothesis, there is no difference.
No difference. All right? So I'm going to show you some more math jargon to help write things down, because what if you have 4 groups or 5 groups or 6 groups, all right? So we're going to write down the null hypothesis to look like this. So this says the null hypothesis is that mu I equals mu j, and this little upside down A, this is a mathematical notation that means for all, or for every, I less than j. All right, so this is a shorthand way of saying all of the means are the same.
For I less than j.
Yeah, so for example, how many, let's pick a number left, 4 groups. If on the right side, if on the left side, this is going to be my I, on the right side is going to be my j, all of my i's are less than each of the j's. That make sense?
So you wrote not equal to, but you mean less than?
No, yes, a not equal to, yeah. Sorry. I less than j.
I less than j.
What? Why?
Because the assumption is that all the groups are the same. That's the
Why would
null.
I need to be less than j?
Because I could write mu2 equal mu1, right? That's redundant.
I was the same.
That's all.
Oh, okay.
That's all. Right? It's just shorthand. This is all shorthand. Okay.
I still don't get that.
Okay. So this gets back to this is like transitory properties. If 1 is less than 2 and 2 is less than 3, then 1 is also less than 3. So if I say, here are my pairs, I have pair 1 and 2, I and j, 2 and 3, right? So if I is less than 2, 1 is less than 2, this I is less than j, and this j, this I is less than this j, then I is also, 1 is also less than 3.
Yeah, no, I get that. I don't understand why it's important to write there.
Because if you have a bunch of groups, you'd be writing out your null hypothesis forever. mu1 equal mu2 equal mu3 equal mu4 equal mu5, It's just shorthand, that's all that is. Don't get hung up on the lingo. It's just shorthand.
It's like loops.
Huh?
Like loops.
It's like a loop. In this case, it's a nested loop. Yeah, it is. It's actually a nested loop.
So the loop.
I is nested with, or J is nested with an I. All right. So what are we going to do here? All right. Okay. The first thing we're going to do whenever we get our set of data, is we're going to do just like we did when we did our regression and our correlations, is that we're going to start doing some exploratory work. We're going to put our eyeballs on the data. Right? We're going to start putting our eyeballs on the data for the same reasons that we wanted to look at the data in the regression case. Right? So we're going to look at things like box plots. We can look at histograms, right? So what's going to drive the difference between the groups? Okay? Things that are going to look at the differences between the groups. So here's what we're talking about is what's going to drive p-values. The things that are going to drive p-values here are going to be things like the observed differences between the group means, the standard deviations in each of the groups, and then the sample sizes. Right? So if I have very large differences between the group means, well, that's actually a large effect, right? That's going to be easier to observe than a small difference between the groups. But if I have a large difference between the groups, but there's still a lot of variance in those estimates, it's going to be difficult to see. I think we drew something like this before. Where on the top drawing here, there's very little variance within each group. The standard deviations within each group is relatively small. Therefore, it's easy to see the difference between these two groups, right? And in this case, it's the same mean between A and B, but here there's more variance in the groups, right? So here it would be more difficult to see a difference between this difference of 30 than this difference of 30. Make sense? Okay. And then as everything, when we learned about power and all that stuff, sample size is going to drive statistical power. That becomes the denominator for standard errors. Okay, so here's the data. So if you're looking at your handouts, to get this plot, I did see where it says box plots? Is there ever documents? It's sort of a little more than halfway down the page. So I did graph box. Box is the command for box plots. Days, the number of days, over treatment. So what this is going to do is this is going to give me a box plot of my dependent variable, days, by each level of treatment, by each level of treatment. What are my treatment levels? Treatment A, treatment B, and placebo. Okay? Does everyone understand how to read a box plot? For those of you who don't remember, let's do a quick refresher. All right. The width, these are called whiskers, the whiskers of our box plot. These tell us essentially, they should give us some idea of the maximum value and the minimum value. Right? So if I'm looking at maximum value and minimum value, what am I talking about? Range. The bottom part of the box is the 25th percentile. The top part of the box is the 75th percentile. If I were to subtract the 25th percentile from the 75th percentile, that's the interquartile range. So range and interquartile range are all measures of what? Spread, dispersion, variance. We're doing the analysis of variance. And remember I told you that regression, ANOVA, t-test, correlation, they're all the same thing? We had that one of those distributional assumptions about our errors. We assumed that our errors were normally independently distributed with an expected value of 0. And what's this thing? Homoscedasticity. Can I make a judgment about homoscedasticity by looking at these box plots? Sure I can. Yeah. I absolutely can. Right? So to my eye, do these groups have more or less the same variability? They have approximately the same range. They have approximately the same interquartile range. Okay. So this, I'm now, just like we did before with regression, when we start looking for the assumptions of our model, I'm going to start with this. All right? I'm going to start with my box plots to say, have I satisfied my homoscedasticity assumption? It looks like I have. It looks like we're pretty good here.
Does it look like placebo has more variance?
Yeah, that's true. And here, the question is it problematically more? Okay. Right, so we'll get into that too. Okay. Does anybody know what this line in the middle of the box is? That's the median. Okay, all right, good. So we know that, right? The other thing that this is going to help us do is, without doing any statistical tests, we can begin to get a sense of what's going to happen when we do our formal hypothesis testing. What do you think is going to happen?
We're going to reject them.
The reject them. Well, what is the null, right? Remember we wrote down the null. It says that they're all the same, right? So this is an important point when we talk about that. When we talk about the ANOVA, is that the ANOVA doesn't tell us if any of the specific pairwise comparisons are different. The ANOVA tests this hypothesis, that they're all the same. Okay? But when we start getting into it, my eyeball is directed to the top, the 75th percentile of treatment A, and that falls below the 25th percentile of placebo, right? So there's little overlap between treatment A and placebo, right? Okay. Is it possible, however, that instead of treatment A, treatment B, and placebo, you could think of this as dose escalation, maybe? This might be the most, what's the word that you would use if you had more of a drug, less of the same drug, no drug. So that would be treatment, that would be drug, not concentration, drug level, what would you call that? Potency. Second?
It's really dose response, I think.
Yeah, that's what I'm trying to get at here, right? So the idea here is, I could also think of these data as if I knew the nature of my data, right? Maybe treatment A and treatment B are the same. This is just 50 milligrams, this is 100 milligrams, this is 50 milligrams, this is no milligrams. So in which case, I no longer have a nominal variable. What kind of variable do I have? It's what? It's ordinal. It would be ordinal. In which case, I can ask different questions of the data. Instead of just asking, are there pairwise differences, I can now ask questions like, what's the linear relationship? Maybe it's not a straight line. Maybe it's a polynomial. Maybe it's a quadratic relation. I don't know, right? So we can begin to think about these things. But to think about your questions in the ANOVA way, you have to understand the properties of your variables. Right? Do you understand what that means? Do you understand what's the property of your variable, the scale of measurement of your variables? Because the higher the scale of measurement, the more interesting questions that you can ask.
Can you give us examples of properties of variables?
So in this case, instead of this being nominal, meaning so this is Zocor, this is what's another cholesterol med? Torvastatin and placebo, right? So those are different drugs, right? So those those would be nominally different. This is, what's the maximum dose of torvastatin? 80 milligrams. What's the minimum dose of torvastatin you would give? 5. So 80 milligrams versus 20 milligrams versus no milligrams because it's a placebo. So in that case, the difference between 80 and 5, we now know that there's some order, right? More, less, least, right? But we don't have to assume that the relationship would be straight. Maybe the relationship looks like that. But the fact that I understand that these are not nominal data, I can begin to look at the trajectory of that dose response. Make sense? Okay. That's an important thing to think about when you're modeling your data. All right? All right. All right, so what does the ANOVA do? This is what we were talking about before, right? So it's essentially, we talked about it being an extension of the t-test, of the independent samples t-test. It's actually an extension of the t-test in general, because I could do what are referred to as repeated measures ANOVA, and you've done repeated measures t-test when you did a dependent samples t-test, when you had the same people measured at time 1 and the same people measured at time 2. Looked at the intra-individual difference, got the average difference. Did you do that? Lie to me and just say, oh, of course. I did that yesterday. Like with my frosted flakes. Okay, so when we look at this, notice the language again I'm using. I have Greek letters, so I must be talking about parameters which refer to population. So I'm not going to say group 1 is the same as group 2. I'm going to say population 1 is the same as population 2. Right? Right? And then the alternative is there is at least one pairwise difference. Okay, all right? The one thing to take into consideration here is that the null hypothesis for the ANOVA doesn't say which of the pairwise comparisons are different. It just says that they're all the same or there's at least one difference. All right, at least one difference, right? So after we do our ANOVA, and if we reject our null hypothesis for the ANOVA, then we can follow up with what are called multiple comparison tests. Or the technical term for it are called contrasts. Contrasts. Okay, so I've been talking about this and talking about this and talking about this. Let's talk about the assumptions of ANOVA. You know all of them. Why do you know all of them?
Because it's a subset of regression.
And a subset of regression is just and you know all those assumptions, right? So we need to review these? Thank God. Because like you're bored of me talking about them, right? But they're all the same. Right? So you don't have to learn anything new. Which is, I don't know. If I were, I'd be like, thank God. I don't hear this blowhard talk anymore. Okay, all right. So what I'm looking at here now is this is the tab stat stuff. See where it says exploratory univariate stats? Okay. This is what I'm looking at here, right? So here I have my, I'm interested in some things here, but I can actually do a sort of back of the envelope comparison of my standard deviations, of my standard deviations to see if I've satisfied the homoscedasticity assumption, right? So in general, what I'm going to do is I'm going to look at the largest standard deviation and compare that to the smallest standard deviation. And if the largest standard deviation is greater than, say, 2 times the smallest standard deviation, then we might have a problem with heteroskedasticity. Right, so that's what I'm referring to here. The other thing here is that it's important to think about this a different way. Analysis of variance. The analysis of variance actually takes a very different approach to looking at differences between groups as compared to a t-test. When we do a t-test, we look at the means directly, right? Like we look at x1 minus x2, right? We do that. Here it's different. I'm going to write down the model here. Before we do that, when you think of a variance, what do you think of? How much you hate statistics, how much you want to do things better, like on a Tuesday, Thursday, I get that. But in words, how would you describe variance?
Maybe like the spread.
Spread of data. So really we're talking about dispersion. Spread. So let's think about this for a minute. Let me write down the null hypothesis again. Right. If all of our groups were the same and we satisfied the assumptions of our model, homoscedasticity and all that sort of stuff, I'm going to draw, that's the distribution of group 1. What would the distribution of group 2 look like? Assuming the null hypothesis. It'd be right on top of it, right? And group 3 would more or less look like the same thing, right? Right? So essentially, if the null hypothesis were true, all of these means would be the same. Not only would all of the means be the same, but they would be the same as the overall mean, right? They have the same standard deviation as the overall standard deviation, right? So when we do the analysis of variance, and you talked about variance being dispersion or spread. Spread from what? from the mean, right? So what the analysis of variance does, it says, okay, I'm going to look to see if the groups are different by looking at the degree to which the group means are different from the grand mean. Right? So let me write that down for you in an equation, and you tell me if it looks familiar. So I have some group mean. I want to see if it's different from the grand mean. What does that look like? Yeah, you got it. Say it. You said it. Say it louder. It's a deviate. This is error. That's what you said, right? Yeah. Analysis of variance. Right? You did say that. I saw you say
Yeah, I
it.
was just sort of surprised.
That you knew that? I'm not. The only thing that's different now is instead of having one subscript, we have two subscripts. Right? That's the only thing that's different. But other than that, I'm subtracting something from an expected value, right? So if all of the means were the same, the deviates of the group means would be the same as the grand mean. All of the group deviates would be 0. Right? Okay. Okay, all right. So here's some notation for the ANOVA. So here I'll talk about these subscripts now. So here you see we have the first introduction of our dot dot. So now I have two subscripts. Okay? So n dot dot is the total number of people in the study. And I'm going to refer to I people within J groups. All right, so now I'm going to write down X, I, J. So I have the ith person, ITH, the ith person within the jth group, jth, JTH. Right? So J tells me how many levels of my factor there are. Okay? So now I have X bar dot dot. So when I say, whenever you see the dot, we take that to mean taken over all of the levels of the subscript. Right? X bar dot dot is the mean of all I people over all J levels. Right? It's just an extension of what you already know. And then group J has n dot J individuals in it. Right? So this is the number of people in the Jth group. We talked about this being individual I in group J. X bar dot J is the mean for the Jth group. Right? S sub J is the standard deviation for group J. Right? So it's just an extension of what you know already. Okay. So if I were to write down the model for the ANOVA, if I were to write down the model for the ANOVA, it's going to look like this. Okay? So now it's a little bit different, isn't it? Where'd the betas go? They're gone. The Yij is still the same here. So this is the expected value for person I within group J. Now the intercept is now mu. When we've seen mu before, when have we used mu?
Population.
Usually represents the grand mean, the overall mean. And this is the Greek letter tau. I use the Greek letter tau to represent a treatment effect. Right? So if I were to write this down again, treatment effects are deviates from the grand mean. Treatment effects, Xij, or X dot J, are treatment effects relative to the grand mean. So, if an Xij is below the grand mean, the treatment effect will be negative. If the treatment effect is higher than the grand mean, the tau of the treatment effect will be positive. Right? And then I still have epsilon ij. Right? Okay. So let me get a simple example here. Have I cloned anybody here yet? Have we done any cloning? Okay, all right. So let's say I'm interested in doing an experiment, and I want to see if I want to compare one intervention versus another intervention, right? What do you think the easiest way to find a treatment effect would be if I were interested in looking at a treatment effect?
Have lots of observations.
Lots of observations. What would if I were to tell you if I could do it with maybe as few as 6? Anybody work with animals? Anybody do rat models or translational studies or anything like that? Okay. We can go across the street to the Wistar Institute and get what?
Rats.
What kind of rats?
Big rats.
Hmm?
Knockout.
What kind?
I said big.
Big, right? They're clones. So if they're clones, they are the same. They are genetically identical, right? Right? They got the same body. It's the same person, rat person, right? Is their body chemistry going to be any different from rat to rat? Probably not. They're raised under the same conditions, have the same diet, get the same amount of exercise. You've controlled everything. Everything, right? So let's do this. At the beginning of a study, I have a set of rats. And let's say that these rats weigh 2 pounds each. Is that a big rat? That's a pretty big rat.
Yes.
That's a big rat, right? And because they're genetic, everything is identical, how much variability is there in this set of data? There's 0 variability in the data. So what does that mean? This means if I were to guess some random rat poll, if I were to randomly select a rat from this, what do you call a pack of rats? A pack?
The pride.
A pride of rats. I thought those were lions. Okay. Well, let's call them a pride. Right? So if I were to randomly select a rat from this pride, and I were to weigh that rat, and I were to say, all of the rats weigh this, would I be right?
I'm going to say yes.
Yeah, because they're all the same, right? Right? Okay, now, let's say that I do a study.
Wait, as a pack or a mischief?
Hmm?
It's either referred to as a pack or a mischief.
Let's go with pack.
A mischief of rats.
Okay, a mischief of rats. Let's call them mischief just because that's fun. Okay? And I'm interested in making a lot of money in vain America, so I'm going to develop a weight loss drug. A lot of money to be made there, right? Okay. So I'm going to take my 6 rats and I'm going to randomly assign each of the 6 rats to one of 2 conditions. 3 of the 6 rats I'm not going to do anything to. They're just going to get what we refer to as standard of care. All right? They're not going to change. Would I expect their weight to change? Now, for all practical purposes, let's say that they don't change. Now, the new rat, let's say our drug works. Right? And let's say that the new rats, the rats that received the new drug, let's say that they all weigh 1 pound each. Okay, now, if I didn't tell you which rat belonged to which group, I didn't even tell you that they were rats. I would just show you these set of numbers. What would you say? Is there any variability in the data? Yeah, there's some variability in the data, right? Now, what we're going to do is we're going to try and use statistical techniques to parse out the source of that variability. Why is there variability in the data? Okay. Now, what I'm going to do is I'm going to let you in on a secret. I'm now going to remove the blind because this is a double-blind study. The rats didn't know what drug they were taking. And until in a couple of seconds, you don't know what drug the rat was taking. All right, now, you ready? Okay, everybody signed their forms. Good. Now we can break the blind. And we see that the rats up here, they got the standard of care. And the rats here got the new drug. Right? So now we can think about variance. We can think about variance as total variance. That's what we had before we put any structure on the data. This is the total amount of variability in our outcome, right? Let's put that structure back on the data. Is there any variability within each of the groups, within each of the levels? No. So there's going to be variability within a level of a factor. Is there variability between the groups? So when we talk about variability between the groups, we're talking about the extent to which the group mean varies around the grand mean. And then we talk about the extent to which the individual scores, the XIJs, vary around their respective group means. That's within group variance. Right? So what we're going to try and do is the ANOVA, the analysis of variance technique, tries to parse out and explain between groups variance and within group variance. If we had variability within the group, can we explain why there's variability within the group? No, the answer is no, because I haven't given you any information. So where do you think this variability goes in our model?
Error.
That goes in our error. That's exactly right. Okay, right? So this is the ANOVA. And oh, by the way, if I have between plus within equals total, you've seen this before, haven't you? Sums of squares. So if I were to do like sums of squares between divided by sums of squares total, what does that equal? You know it. It's the R squared. It's all the same stuff, guys. It's all the same stuff. Right? Instead of having x bar dot j when we did regression, what we did was xi, or yi minus yi hat. Remember we did that? What's yi hat? That's the expected value of person I, right? Well, if I'm in group J, and all I know about you is that you're in group J, what's your expected value? The mean of group J. It's the same stuff. Right? It's the same stuff. It's exactly the same. Okay, so then our test statistic for the ANOVA is the F statistic. F. I don't know why F, but F. Doesn't have anything to do with cursing or anything like that. But essentially what we're interested in looking at is the analysis of variance. We're interested in looking at the ratio of the variability due to between groups variance. How much variability is there between groups? Think of that as a signal. How strong is the signal? Relative to how much variability there is within a group. Think of that as noise. So it's signal to noise. It's a signal to noise ratio. Right? So if we were to go back to our big fat rats, and we maintain this structure that we put on the data, can we explain the variability in the data? Where is all the variability in it? Is there any variability within a group? No. So if you're in a group, I can predict your weight perfectly, right? So given that there is some overall or some total variability in the data, all of the variability in this case is due to what? Between group differences. There are no within group differences. Now this data never happens. This would never happen. But you get the concept here, right? So if you think about this as the difference, the variability between the groups is signal, right? Variability within the group is noise. You haven't explained that variability.
Is that why you said you started at the beginning by saying, how can I make sure that I get a signal? And that's by having clones.
Yes.
And getting rid of the within group.
Exactly. Right? So if you want to maximize the statistical power of your study,
Decrease the within.
go across the street and study genetic clones. Twin studies. That's why twin studies are so powerful in medicine and epidemiology, is because you've essentially held a lot of that intra-individual biological differences constant. Right? Make sense? Okay, all right. And then remember we were talking about reference distributions, probability distributions yesterday? We did the T distribution and the Z distribution. There's the F distribution too, right? And how many F distributions are there? There are an infinite number of F distributions, right? Okay, so how do we do this, right? That's what you guys always want to know. Well, it's really simple. There are two ways to do a one-way ANOVA, a one-way fixed effects ANOVA in Stata. One of them is simple. It's just ANOVA. That's the command. Then your dependent variable, and then your factor. Right? And this is the output. Right? So, what do we have here? We have the root mean square error. This is the same root mean square error as we got when we did regression. Right? So this is the standard deviation of the error around regression line. What the hell is regression doing here in ANOVA? The same thing. Right? We have our R squared. How did we get the R squared? Well, I took my treatment sum to square, divided it by 94. So if you got a calculator, do 34.7 divided by 94, you ought to get that. It's the same thing. Here's that word. Partial sums of squares. Partials, right? So sums of squares. Degrees of freedom. MS, this is not multiple sclerosis. This stands for mean square. How do we get the mean square? We're going to take our sums of squares divided by the degrees of freedom. Does that sound familiar? Sums of squares divided by degrees of freedom. Variance. Right? How would I write down the formula for variance? Right? You've seen this before? Sums of squares divided by degrees of freedom. Sums of squares divided by degrees of freedom gets me a mean square. This is variance. Mean squared is variance. The other thing that you'll notice here is this one thing I like about Stata is that the title's on there, this on our ANOVA table. We're talking about the sources of variability. The source of variability. And then we have our F statistic. How did we get our F statistic? I just told you it was a ratio of the treatment variance to the error variance. So if I were to divide 2.7 into 17.4, I get 6.45. This is my p-value associated with this. What is this p-value or this F statistic actually testing?
Just the null hypothesis.
And what is the null hypothesis?
That there is no difference between across the means.
Across all of the population means, right? So, this is statistically significant. This says what? There is at least one difference, right? Now, I will tell you this. This p-value can be significant, statistically significant, and you could not see pairwise differences in the end. That happens every once in a while. It's rare, but it happens. Because this is an omnibus test. It's actually testing a different hypothesis than each of the pairwise comparisons. Right? So why would we do the ANOVA, by the way? Does anybody have any insight as to why we might be interested in doing an ANOVA, and instead of this case, we could do 3 t-tests? All right. Keep that in mind as we talk about it more.
Do 3 t-tests do all the permutations of the differences?
Yeah, so what's going to happen is that you can do, if I have k categories, the number of possible comparisons will be k times k minus 1 divided by 2. Okay? And what happens is that as k increases, the number of pairwise comparisons increases. The alpha rate explodes exponentially. I have a graph of that. I'll show you what happens graphically, what happens here, all right? So the thing to think about here is, where did all of these degrees of freedom things come from, right? Okay. So the degrees of freedom for the groups is going to be k minus 1, right? When we talk about deviances, what should happen if I add up all of my deviances? It should be 0. So if I were to think about this as deviates and this as deviates, these should all sum to 0 and this should sum to 0. Remember we cut up a piece of pie? By the way, it's Pi Day 314. Happy Pi Day. Nerds, all of us.
Oh.
No? Nobody got that? Okay.
That's big.
All right, anyway. In this case, we have 3 groups, right? 2 of those 3 groups could be whatever they want, but that third group has to remain constant. Right? Same thing, All right, well, let's keep going on here. So if I use the one-way command for stata, I can only use that for one-way ANOVAs. That is, if I only have one factor. The one-way command will also do a statistical test for the homoscedasticity assumption. It'll do something called Bartlett's test. So the probability for the p-value for testing to see if the variances are different is it's pretty big. Right? So there's this Bartlett's test. I'm going to tell you right now, you can effectively ignore this. Because as soon as you start getting sample sizes of any sort of any substance, you will always reject this. These become overly sensitive. Right? The eyeball test is rock and roll. Let's do that one. Okay? Okay, so let's stop here, and we'll pick this up on Tuesday. So what I'd like you to do for your homework assignment is just like we did for regression, right? In the literature, see if you can find a paper that uses ANOVA. There are lots of different kinds of ANOVAs. This is the most basic one. And see how people are using ANOVA. See if they've talked about any of the assumptions, any of that stuff, and come in Tuesday prepared to discuss your article. Fair enough? Okay. I'll go and I'll put this presentation on Blackboard today too for you, as well as the code. Okay.